Hello everyone, welcome to 𝗨𝗏𝗧. So after a long gap, we are now coming back with this new series, and in this series I'll be explaining the design, analysis and design of RCC box culvert. So basically for this particular series we'll be using, if you can see here in the left side, this example. It's a single cell RCC box culvert, okay, and we'll try to analyze this culvert for different loading conditions, including the dead load, the live loads, which are actually the you can say vehicle loading as per Indian standard. We will see the estimation of the soil pressure, and we'll also see the estimation of the water pressure from the inside. So all the loading conditions we will apply here, and we will also, I can say, see the design criteria as per IRC 112. Okay, so it's a complete I can say a package that you will be finding in our YouTube channel. So let's get started. So here, if you see in this example, we have a box culvert which has the inner clear dimension of 4 meter by 2 meter. So 4 meter is the width here, 2 meter is the height, clear height. Okay, then we have the top slab, we have the bottom slab, we have the side walls, and we have small haunches here which is of 150 by 150 at all the four corners inside. Okay, and then we have this approach road, we have some road crust above, right, and the filling from the side, correct. So here when we will be you can say designing or analyzing the structure, so basically we'll be considering this bottom top slab and the side walls. We'll ignore the effect of this small haunches 150 by 150 because it will hardly add any I can say structural stability, or I can say structural strength to this whole I can say element. So we'll be ignoring this in the structural analysis and design. Okay, and so basically we'll be you can say using the very classic theory of analyzing the box culvert, which is the 2D analysis. So we'll be creating a 2D frame to analyze this box culvert. Okay, so what are the different features of this box culvert if I see? So here for our example purpose, we are considering the thickness of the wall as of now, which is of 400 mm both side, and also the bottom and top slab we are considering of 400 mm. Okay, the clear dimension is 4 meter by 2 meter, correct. Okay, the clear dimension is 4 meter by 2 meter. So when we'll be modeling this I can say frame in a software program, whichever software program we'll be using, so in that case we'll be modeling the center line of this particular frame, correct. So if you want to find out the center line, so for the top slab, if I just draw the two ends, it will be the center line, correct, something like this. And here for the bottom slab it will be something like this, and for the wall also it will be this center line. So we'll be modeling a frame like this, okay, in 2D. Okay, and then our bottom slab is supported on the soil, right. So what we will do, we will divide this bottom slab into some equal segments like this. Okay, so we will be creating some nodes in between intersecting this frame, and then we will be assigning some springs here. Okay, point springs, estimating the stiffness. We will also see how we will be estimating the stiffness of these springs. So that will be explaining here. So now first of all, if I see the center to center dimension, so what will be the center to center dimension? So this center to center dimension here, it will be, see, the clear dimension is 4 meter, and then we have 200, half of this whole thickness, so it is 200, this side 200, so 400 as a whole, so it will be 4.4 meters, right, this dimension. And if I see the height, so this will be my 2000, that means 2 meter plus 200 plus 200, so 2.4 4 meter height wise. Correct. So this will be my center to center dimension which we will be using for the modeling purpose. Fine. And so this is the cross sectional view that we are seeing. So if I want to draw the actual top view of this, so it is basically something like this. Suppose this is my culvert. Okay, this is my culvert. We have the nala here. Okay, and we have the road along this direction. Okay, so if I just want to draw the water flow, so this is the water flow, right? So there will be obviously a nala, right? So it will be something like this, and this is my traffic flow. This direction will be my traffic flow. Or I can also write it as traffic direction. Correct? Traffic direction. So this sectional view that we are seeing, it is basically something like this. Okay, this is the section. Suppose this is section A. So this is the section A that we are seeing. Why we are analyzing this? Because the major load, the traffic direction is this way. So the wheel loads will be like this. Okay, so the major load will be in this direction, right? In the transverse direction, it won't affect much, right? So generally, whenever we design box culverts, we always go for a 2D approach. It's the very simple and easy approach to do. Okay, so 3D analysis is not required actually for this kind of box culverts. Maybe it is single cell or multi cell. 3D analysis is not much required. Okay, so so we are taking a strip. Suppose we are taking a strip of around 1 meter, right? 1 meter strip per meter width we are finding. So we are finding out taking this 1 meter strip here. Okay, and taking this 1 meter strip, what we are doing, will be modeling this. So whatever thickness we are considering for this, we will be applying the thickness 400 400 400 for all the slabs and walls, and along the other direction, this direction, it will be of 1 meter per meter width. Okay, so but the actual width of this culvert or actual length of this culvert along the direction of the water flow, if you see across the traffic direction, so it is basically, for this condition, we are using 22 meter. And along this direction only we will be having the carriageway width. So depending on the carriageway width, we will be deciding which vehicle load combination or how many vehicle combinations we need to consider for design, right? So it totally depends on this particular width. Okay, so maybe we will have some you can say parapet also. So after this parapet, if you have the pedestrian you can say way, so pathway, so in that case you can remove the you can say width of the pathway, and then whatever is left will be your, you can say carriageway width. But here we are not considering any pathway and all. So after this you can say the parapet walls, we can consider the pathway. So this parapet wall, suppose we are considering of 450 mm. Okay, both side, right? So that means 900 mm. So if you you can say deduct 900 mm from this 22 meter, so in that case the rest will be your carriageway width. Fine. So here for the road crust, you may have, so if I just write it here, when we have this kind of culvert, so the road crust, it can only have wearing course or wearing coat, I would write wearing coat, or it can have both wearing coat plus your road crust. That means the different fields, right, that you need for the road. So wearing coat plus road crust. Okay, so it depends. in our case, what we will do, we will have this condition, the second condition, where we will have the wearing course and the root crust both. So the wearing course we will be having of 50 mm. So I will write it in meters, basically 50 mm. Okay, and the fill, okay, for this fill, that means the root crust, actual root crust, it will be of 600 mm. So 0.6 meter to 600 mm. Okay, so the total root crust thickness will be of 650 mm. That means mm. So that means 0.65 meters. Okay, so this we will be you can say using for the calculation of the superimposed dead load on the slab. But when we'll be applying the live loads, that means the vehicle loads, so we need to find out the dispersion width. So for the estimation of the dispersion, we will only consider this wearing coat or wearing course, rather considering the wheel fill also, to get the maximum you can say loading criteria. Okay, so more critical loading criteria. You can say that if I have the root crust, then why should I, but you sometimes maybe the root crust is removed for some reason and only the wearing coat is used. So in that case, the loading condition will be changed. So that's why the most critical loading condition we can consider for this design. Okay, so this we will be discussing later. First we'll more focus on the, you can say, the modeling of the structure first, okay, in this lecture. So the grade of materials, as it is a concrete you can say box culvert, so the material grade, that we will be using for concrete, it will be M35 grade. You can use whichever is as per your specification. So M35 grade. So whatever specification you require to define this concrete, so for that you can refer IRC 112. So if I just take you to IRC 112 2020 and page number 31, you will find this table number 6.5, where the different you can say parameters to define the certain you can say the particular concrete material. Okay, the particular concrete material, you will find all these parameters here, and accordingly you can define the concrete in your software model, you can say in your software program. Okay, so it is for concrete. So I'll just write it here, table 6.5 IRC 112 2020. Okay, this will be using. And for rebar steel, we'll be using Fe 500 grade. Okay, so this will be my material grade for the particular design and analysis will be used. Fine. Okay, so first let us jump into the software and let us model this. We need to model a box frame of 4.4 meter by 2.4 meter. So I'll just go to my software program, and for this program, or you can say for this series, we'll be using Midas Gen 2026 actually. Okay, so why I'm using Midas Gen 2026 or 2025, whichever is available with you. So you may say that most of the cases for analyzing the bridges and you can say culverts, the Midas Civil is being used, but then why this Midas Gen I'm using? So those who are into building sector and you are using this software for the building analysis, and you obviously you may have to design the box culverts in many of the projects. So in that case, only for a box culvert analysis, you don't have to go for the whole bridge software. You can also do the same analysis here. Okay, so you just have to do some manual intervention here. So that's totally fine, I believe. So I am going to show you a very classical method of analyzing this box culvert here in this Midas Gen. Okay, so first of all, using this view toggle, so I'll just change it to the top view. And what I will do, I'll create the nodes here. Let me just do one thing. I hope it will, yeah, okay. So what I will do, first I will create the nodes. So I have the length of 4.6 meters. So I'll just in this main menu, I will go to node and element. If you see this ribbon, okay, node and element, and I'll click on create node. So first I will create a node at 0, 0, 0. Okay, so the coordinate and the distance will be 0. I'll click on apply. I'll close it. So you can see one node is being created here. I'll take this select by window. I'll select this here in the ribbon for the nodes. If I go to translate here, I can translate this node along x. So you can see dx, dy, dz. So I'll give this dx as 4.4 meter and click on apply, and you can see another node I have created. Correct. Now what I will do, I will go to, okay, it is asking me to save. Earlier I have modeled one, so I'll just name it as, see, auto save automatically. It is asking for saving the model. You can also save by yourself. I'll make it as 01. Save. Okay, will take bit time to save it once. Yeah, so now I will go to my isometric view using this arrow, and see the other node I am not able to see. So what I will do, I will just scroll my mouse wheel once, and once you scroll and leave it, and then you move your mouse like this. So in that case, what will happen, it will zoom in and zoom out. Okay, so you can see now I mean zooming out. So like this. Now if you click on the mouse left button, it will be the zoom option will be gone. So now what I will do, I will again take my select by window. I'll select these two nodes, and now I will make the x as 0, and I'll make the z, that means our vertical axis, it will be as 2.4 to create the height. Okay, I'll click on apply. So you can see these 4 nodes for the frame I have created. I'll close it. I'll go to my front view using this option, using this area. So I'll just click on here, this front view, and you can see these 4 nodes here, right? I'll just zoom out a bit. Okay, now I will go to structure, and before going to model this, let us define some section and I can say material. So let us go to properties here, material properties, and I'll click on add. I'll change this to concrete. I'll change this to IRC, and here in the list you will find this M35 grid. Okay, so all these parameters you will find in the IRC, you can say 112, and the software also takes automatically. Okay, so you don't have to put the values from the code. It's taking already, because this is already you can say listed in the software. Okay, so M35 grid, I'll click on OK. Fine. Now to define the sections, so what I will do, I will define different sections. So I'll just go to section, I'll create add, I'll change it to user, and I'll change it to box section, solid rectangle. Suppose I will name it as top slab. So I'll just name it as, suppose, TS top slab 400 thick. Okay, I'll make the depth as h as 0.4 meter, that means 400, and this width I'll make it as per meter width, so 1 meter. Okay, so it will be something like this. The offset I'm not going to change because we are modeling the center line at the center line, so I'll keep it at the center itself. I'll click on OK. Now I will make a copy. Obviously all our thickness are all of same thickness actually, but I'm just creating separate you can say sections for the walls and the different slabs. Okay, so that later on if you want to change, you can just modify this rather defining another one and assigning it to the particular element. Okay, so I'll make a copy of this. I'll select this, modify, I'll make it bottom slab, so I'll make it as BS, same will be okay. I'll make a copy, sorry, one copy, and I will modify this and I'll make it as sidewall. So I'll make it like this, SW 400 thick, it will be same. Okay, right? So I have top slab, bottom slab, and SW. Now I will close it. So you can see material section. You can also define the section from here. If you go to section properties here, the same window will open actually. Okay. So now I will go to node and element. I'll go to create elements, and here I'll select the grid of concrete. I have only one grid, so it is selected. Now I want to model the top slab, suppose. So I'll select TS from here to here. You can see it is modeled. I'll change it to bottom slab. So I'll say model from here to here, and I will change it to side wall. So I'll make it from bottom to top, bottom to top. Okay, I'll close it. So what I have done, I have modeled the box with unit width and thickness of the slabs, and the walls are of 400 mm. Okay, you can also turn off this rendered, or you can say the hidden view. So if I go to my view and you can see this hidden view, you can toggle this, so you will be seeing only the line, right? So if I go to my front view here, so this is my box, correct? Okay, now this bottom line is defining actually it's actually representing my bottom slab. So I have to assign the soil springs here in the bottom slab. Okay, so for that, what we need to do, we need to estimate the soils springs. Okay, so I'll go to my whiteboard, and let us first consider the different parameters that we'll be using for the soil. So I will just write soil parameters. Okay, so the SBC, allowable safe bearing capacity, which we are assuming. Okay, so suppose we are assuming SBC of 150 kilonewton per meter square. Or this parameters you need to get from the geotechnical investigation report. Okay, then we have the angle of internal friction. Okay, angle of internal friction. So this angle of internal friction we require for the you can say the backfill. Okay, so because we will be estimating the soil pressure from the side on the side walls, so for that we need this angle of internal friction. So this is for backfill. Okay, and we define it as with phi, which is we are considering suppose 30 degree. Okay, so depending on this, we'll be finding out the K0 or K, whatever we require. Okay, the earth pressure at rest or the active earth pressure. So we need to find this angle first to estimate those, right? So suppose as per our soil report, it is 30 degree, and then we need the unit weight of soils, unit weight of soil fill. So suppose here we are considering it as 20 kilonewton per meter cube. Okay, we are considering it as 20 kilonewton per meter cube. So once we have this data, what we need to define is the point springs. So if you see, if I just take a small corner of the culvert, so we have these nodes. We need to create some nodes actually. Okay, like this. Okay, and here we'll be assigning the springs like this. Okay, maybe we'll be defining the corner springs as K1, the stiffness of the corner spring, and stiffness of the internal spring will be defining it as K2. Okay, why I'll be explaining in a while, why I am defining it in two types. So these soil springs will be defining. So now here for our design purpose, the soil spring that we'll be estimating, we'll be using the Bowles formula, which is given in the foundation analysis and design book by Joseph E. Bowles. Okay, so the modulus of subgrade reaction. So basically this stiffness will be finding out using the subgrade modulus, right? subgrade modulus. So this subgrade modulus we will be getting for the area as area spring stiffness, and from that we need to estimate the point spring stiffness. So I'll show you how it is being done. So subgrade modulus, generally what we do, we use this formula K S equal to QA by delta, which is your allowable settlement. Okay, now in 𝗏𝗏𝗡's book, if I just open this, if I just open the 𝗏𝗏𝗡's book, sorry, yeah, here. So here they have I can say that the author have recommended this formula for the SI unit, which is 40 into scale, you can say safety factor into QA, which is QA is nothing but the you can say allowable safe bearing capacity. Okay, so this safety factor, when we are multiplying with the safe bearing capacity, it is basically giving us the ultimate bearing capacity or the ultimate bearing pressure. Okay, so if you see, you can see here QA is equal to Q ultimate by scale factor. So when I am putting this Q, if I am replacing this QA with Q ultimate is scale factor, the safety factor. So the safety factor will get cancelled. So it will become 40 into Q ultimate basically. Okay, so as it is the ultimate, you can say safe bearing capacity, ultimate bearing capacity is being used. So you can see here many have this doubt that while sizing the foundation, shall we go with ultimate bearing capacity? So you can see here that it is clearly written. You can see where it is. Yeah, it has been found that the bending moments and the computed soil pressure are not very sensitive to what is used for KS. Okay, because the structural member stiffness is usually 10 or more times as great as the soil stiffness as defined by KS. So it is saying that this spring stiffness that we will be defining, it doesn't much change the structural response, or you can say the structural behavior, the bending moment and all, because the stiffness of the structural element used to be generally 10 or more times higher than the soil stiffness. Okay, so recognizing this, the author has suggested this following approximating KS from the allowable bearing capacity. Okay, so this KS is defined from the allowable bearing capacity, and a safety factor is multiplied to change it to ultimate bearing capacity. So this is basically to find out the bending moments. Later on, if you see this 40, if you see here, it is written 40 is reasonably conservative, but smaller assumed displacements can always be used. So you can use a smaller value. Okay, so to have a conservative approach. So generally, when you will be sizing the foundations, as per my understanding, this scale factor is not required, but for the design, to get a conservative you can say design, you can use this formula 40 into SF by QA. Generally what we do, we mostly foundation design, we use QA by delta. Even if you go to the upper portion of this particular document, you'll see the KS is defined by Q by you can say delta. Okay, so basically what I will do in this particular lecture, will be using this stiffness, spring stiffness or the subgrade modulus formula, just to you can say estimate the bending moments, I mean the structural responses, the bending moment shear force, but for the base pressure check we'll do it manually. Okay, so here the KS equal to 40 into SF into QA. So I will just write it here in my whiteboard. Subgrade modulus formula by Bowel, it is Ks equal to 40 into safety factor into my allowable safe bearing capacity QA, and it is in kilonewton per meter cube. So basically it is not kilonewton per meter cube. We can say that this is in kilonewton per meter square pressure corresponding to the per meter settlement. Okay, so it is something like this, so which we can write it directly kilonewton per meter. So now if I want to find out the subgrade modulus, so I have the QA with me, which is this one. This is my QA. Okay, I have this constant, and now I have to find out this, you can say, the safety factor. Okay, this safety factor. So for this safety factor, we have a recommendation in IRC 78. Okay, so if I just open IRC 78 and I'm using this version of part 1 2024, here in this clause 706.3.1.1, it says for foundations and the well foundations, for open foundation and the soil foundations resting on soil, the allowable bearing pressure on ultimate bearing capacity may be taken as 2.5 for soil. So this is the safety factor 2.5 that we'll be considering here. Okay, so it is as per IRC 78 part 1 2024, right? I'm using. So if I just jump into the my whiteboard, so IRC 78 part 1 2024, so the safety factor that we'll be using as 2.5, correct? So now if I just estimate the Ks equal to 40 into 2.5 into 150, it will be in kilonewton per meter cube. So here what will be the Ks value? So if I just open my 𝗀𝗁 and I will calculate this, 40 into 2.5 into 150, so it is around 15,000. So 15,000 kilonewton per meter cube. Okay, it is the same thing if you consider 25 mm settlement, okay, and with a safety factor of 2.5. so you can see here, if I just suppose I am using Ks equal to QA by delta into safety factor. Okay, and this delta I'm considering 25 mm settlement. Okay, so if I just write it like this, 150 kilonewton per meter cube, delta is 0.025 25 mm, and 2.5 my safety factor. So how much I am getting? You see, it should be the same. So if I just write it, 150 by 0.025 multiplied by 2.5 safety factor, you can see it is the 15,000. So it is basically written in the Bowel's book, if you see here, that the delta H is actually 0.0254 meter or 1 inch, which is considered, okay, for this formulation. So hope you understood how it is being done. So it is not a, it is just a formula to directly give you this rather dividing and all. Okay, so now we have this you can say spring stiffness. So this spring stiffness that we got, it is basically for the area. So if you see here, it is on kilonewton per meter square per meter settlement, but we have a node. So suppose we have an area like this, okay, and we have a node here at the center. So whatever force we have in this area, we want to concentrate here at this particular node. So what we will do, we will apply, what we will do with the area force. So suppose this is W, we will do W into A, then we will get the point force, correct? So here also same, we have the subgrade modulus for the area. Okay, now what we will do, we have to multiply this A and B here with this. Okay, Now we know we are designing it, analyzing it with the 1 meter width. So B will become 1 meter, 1000. Sorry, I will just write it here, 1 meter. But how much will be the A? So for the internal, you can say, sorry, for the internal nodes, the A will be because the tributary width of this, so half of this side, half this side. So this will be the A, right? And for the corner node, only half of this side will be the A. So it will be A1, it will be A2, right? So in that's why I have you can say named it differently, because the corner nodes will have a smaller tributary area because it doesn't have other side, right? But the internal have both sides, so the tributary width will be this side and this side, half of this side, half of that side, right? So that means it will be similar to the node to node distance for the internal one. So first of all, we need to create the nodes with an equivalent, equal spacing. So what I will do, I will jump into my model and I will go to my select by window. I select this bottom member. I'll go to you can say node element, and under this element I will go to divide, and I will click on this frame here because it's a frame element. I'll select this equal distance and number of divisions I want to make, suppose 25 divisions. Okay, you click on merge duplicate nodes if there is any duplicate node created, so it will be merged. So I'll click on apply, and you can see we have created this nodes. So what is the node to node distance? So if you see this node at the end, so you can see the coordinate here. So this node is at 0 0, the other node is at x equal to 0.176, and it will be 352. So that means the node to node distance we have defined, it is 0.176. So if I just again go to my you can say whiteboard, and if I want to define this A, we are getting 0.176 for the internal nodes. Okay, so here the A2 equal to 0.176, and the A1 it will be 0.176 by 2, correct, because half of this we are taking, right? So now then we can easily find out the point spring stiffness. So for internal nodes Ks, suppose point spring, so I'm making as Ksp is equal to how much it will be? So the Ks will be 15,000 multiplied by, my width is constant, this dimension is constant, 1 meter, multiplied by, for the internal it will be whole, right? Half of 0.1762 0.176, half of 0.176, so as a whole it will be 0.176, correct? So it is 0.176, and if you see here, this is what will be the unit. So this is in kilonewton per meter cube, this is in meter, this is in meter. So meter, meter, meter square, so this will be cancelled, so this whole unit will become in kilonewton per meter. So that means this much kilonewton force at a point for per meter settlement, like this. Okay, so for external, so let me find out this value. This value will be how much? If I just open my you can say calci again, so 15,000 multiplied by 1 multiplied by 0.176, it will become 2640 kilonewton per meter settlement. So here again I am writing for the outer, or maybe for corner nodes, Ksp will become half of this, so it will become 1320, correct? 1320 kilonewton per meter. Why it is half? Because the formula will be like this: 15,000 multiplied by 1 multiplied by 0.176 by 2. Correct? So it is 1330. Okay, so this is the spring stiffness that we need to define, assign to this particular nodes. Okay, now remember, when we are modeling this box in the software program, we are doing 2D analysis. We'll be applying some lateral forces and all, but we are not defining any lateral stiffness of the soil here. So in that case, it will give you instability error, because will be defining only spring stiffness along the vertical axis. Right, will not be defining anything along the horizontal. So in that case, what we need to do, we need to assign a small lateral support here. So only a lateral support will be assigning at one node, so that we do not get instability error in the software program. Okay, so let us now jump into the software. So for this corner node, it is 1320. So now to assign the point springs, what I will do, I will use this select by window. I will first select the corner nodes. Okay, and then I'll go to, you can say, boundary here and the ribbon menu, and I'll go to point spring. I'll click on point spring. So here you can see I need to define the spring stiffness, but along which direction I need to define? Obviously for this point will be assigning along the Z. So always the Z axis is the vertical axis. So in that case, we'll be assigning the spring along the HDZ. Okay, only for the you can say translation. So what I will do for HDZ, for the corners points, it will be 1320. This is the spring stiffness in kilonewton per meter. I'll click on apply, and then what I will do, I will select this internal nodes and I'll make it to 2640 and click on apply. Okay, so now we have assigned the soil spring stiffness to this base slab. Okay, so if you see in the isometric view, this is my simple frame that I have created with the springs. Okay, you can also again see the hidden view like this. Okay, this is the divisions we have created, 25 equal divisions, right? I forgot to assign one more thing here. As I have already discussed, we need to assign a lateral support at one end, so that we do not get instability, as we'll be applying the lateral forces for braking force and all. So what I will do, I'll go to the front view. I'll turn off this hidden view option, and I will take my select by window. I will select this window, this node. I think these two nodes are selected. Let me just, yeah, now let me select this node only, and then I'll go to boundary. I'll go to define supports, and I will see this is along x direction, so I will just restrict this dx. Okay, I'll click on apply. So you can see here I have applied a lateral support also along this direction, and we have this spring stiffness in all this direction. So I will keep this lecture up to here only. In our next lecture, we will see the estimation of different loads. Okay, what are the expected loads that can come on this particular you can say culvert, including the live loads, the soil loads, all these things, the estimation and application in the software program, both we will see in this series. So if you have any doubt in this particular lecture, you can always write me in the comment, or if you have any suggestion, please do write in the comment, so that I can improve my lectures or improve the videos in the further videos. Okay, thank you, and we'll see you in the next lecture.